to have one of our own graduates again visiting us. Tekin is working as an assistant professor in Bilkent, and his area of interest is learning data science, online learning on multi-armed problems, very hot topics these days. He received his bachelor's degree here with us as the first ranking student in 2008. He did his master's and PhD in Michigan, University of Michigan. He obtained his PhD degree in 2013, and since then he's been with, so he did a postdoc at UCLA, and after that he's been with Bilkent. Please join me in welcoming Cem.
I'd like to thank Professor Tekin for very much for this kind invitation, and it's a pleasure for me to be at ODTÜ. So today I'm going to talk about my research interests, which is basically online learning in big data. So I'd like to mention that this talk will be about basically decision making under uncertainty and online learning. So as you know, there are many aspects of big data, but this is related to the learning aspect of big data. So when I mean big data, what I mean is high-dimensional, non-stationary, and streaming data. So it's not available at the beginning, but it's coming on the fly. So I'd like to start with a few examples, a few example applications. So consider, for instance, recommender systems which exist in today's internet. Consider, for instance, YouTube. So if you know YouTube, you have seen these recommended videos. So it has some algorithm to come up with video recommendations based on your past searches on YouTube. So we can model this as follows. So there is a user which comes to the YouTube. It has some features, some past information such as the browsing history, IP address, likes, dislikes, and so on. So the YouTube recommends a set of videos, and based on that, the user gives a response by basically clicking on some of the videos. And here, the goal, of course, is to make the best recommendations to the current user, but there is also a conflicting objective, which is to improve recommendations for future users. So we would like to optimize for the current user, but we would also like to learn from the current user, such that we can use what we learned for the users that will come in the future. There is another application which is personalized treatment. So as you all know, the success of a treatment, medical treatment, not only depends on the type of the drug, but also on the amount of the drug and when the drug is given and so on. And this is affected by the status of the patient, such as the genetic factors, the kind of the disease, age, and so on. All right? So we can model this as follows: a patient's visit to the doctor's office. We observe some features of the patient. Then doctors administers a treatment, and the patient basically responds to the treatment. And we'd like to give the best treatment to the current patient, but at the same time we also like to learn about the best treatments for future patients. So these examples can be generalized. So there are many applications that has the same format as what I described in, say, telecommunications, for instance, for routing, for intrusion detection, or in online learning like personalized course sequences and so on, or in social networks, such as item recommendation, influence maximization. So all of these can be modeled as online learning problems that involves uncertainty. So we can have a mathematical formulation of a universal mathematical formulation of all these type of problems. Basically, in all these problems, we have the following. We have a set of actions. We assume that we have k different actions, and we have decision epochs. So at each decision epoch, we basically observe some context. This can be viewed like a state of the environment. And based on this, we would like to take an action. So it's basically learning through repeated interaction. What we do at epoch T is to observe the context, take an action, and then we observe the reward that is related to the taken action. But what we do at round T+1 is again the same thing, but now I'm taking action at the time T+1. We would like to use the knowledge we have gained up to round T+1. So this is where learning takes place. And we can define our goal as, say, maximizing the cumulative expected reward, or maximizing the reward with high probability, and so on, for any given time horizon. So the important point here is that we may not know what the time horizon is, so we'd like it to be good for all time horizons. Okay, so how can we model the problem that we face at round T? So I have an entity that is called the learner. The learner observes the features, which is the context, and the context can be high dimensional. Assume that there are D types of features. Each feature can be categorical or real valued. And I assume that these features are exogenous, which means that my actions do not affect these features. Okay? So the learner now would like to take an action. But the problem here is that we don't know the expected returns of these actions. And we also don't know the distributions of these rewards of these actions. Okay, so the actions yield random rewards. So that comes from a distribution that depends on the action and the context. But we don't know the distribution. So the problem is basically how can we learn the actions that maximize our expected rewards over time by just using the feedback that comes from these random observations. Okay, this is the problem. So you might ask, this talk is about big data, but where is the big data in this model? So what we have is the following. Consider a recommender system, for instance. We have basically many different features for the user. So it's a very high-dimensional problem. And as you know, learning in high-dimensional problems suffers from the curse of dimensionality, which means that you need a lot of samples to learn accurately. So the question is, can we learn the features that are relevant, the features that affect the rewards, such that we basically reduce the problem to a lower dimensional problem? Or another problem is, consider for instance Google. To Google, around 40,000 queries arrive per second. Okay, so it needs to respond very fast, and storing all these information, past information, also is challenging in terms of memory requirements. So that the idea is, can we quickly update our algorithm such that we use all up-to-date information to give a new recommendation to a new user. Another challenge is now the number of items can also be very large. So how can we learn in that setting also? So these are where big data comes into play. As another application, if you consider these personalized treatments, now again the context has many dimensions. But there could be also many treatments, there could be combinations of treatments, and we need to learn these combinations. But sometimes you also need to take into account the safety when learning. So basically we would not like to explore a risky action, because that can put the patient at a risk. So there are many areas that these learning problems can be applied to, including big data streamlining, to communication systems, cognitive radio networks, to recommender systems, and so on. So what I'm going to do is that I'm going to basically give an introduction on how these problems are solved, how learning is performed. And this introduction will involve both works of other people and my work. So I'd like to explain basically how we deal with several challenges in this online learning in big data. So the first challenge is how to learn as data grows. So the problem is to take an action at time t, we can use all the information we have gathered up to time t, which consists of all the contexts, all the actions, and all the rewards observed prior to time t, and the current context. But now this history grows linearly in time. So if you consider that Google example, each second introduces 40,000 new samples. So that means that keeping the entire history is very inefficient. So offline learning is not feasible. Offline learning is like SPR, neural network, logistic regression. Okay? So what offline learning does is basically it looks at the entire history, the entire data, it takes the entire data into account, it basically produces a decision rule, and the actions are selected according to that decision rule. So in contrast, in online learning, what happens is the following. Now, I construct my decision rule at time t-1. I have that, and I have new observations that arrive. So my decision rule at time t can be constructed by just looking at these observations, my old rule plus my new data. So therefore, I don't need to keep the entire data in the memory to learn. And of course, an important question is, can we achieve the same performance if we use an online rule instead of an offline rule? And under some problems, under some cases, we can achieve this. Okay. And there is also another important distinction that makes this actually different from supervised learning, the classical machine learning. So let me give the example. So learning with full feedback means the following. As soon as I'm making predictions, so I'm making predictions about the weather. So assume that I made a prediction that it's going to be rainy tomorrow, heavy rain, but I can observe that tomorrow that actually the rain was light. So I can calculate the loss due to my incorrect prediction, right? But I can also calculate the loss due to any other prediction that I could have made. So if I predicted something else in the past, knowing the truth now, I can compute its loss also. So this means that I can have this counterfactual information. But now, in most of the problems in online learning, we have what is called banded feedback or partial feedback. So it means the following. Now, consider another example in which I administer a drug to a patient, and then I see the response of the patient and record the loss for the patient. Here I cannot know what would have happened if I had given drug B to the patient, right? Because that information is not present. So basically my actions also limit how I acquire information in this case. And this is what banded feedback means. So there is actually in banded feedback an inherent trade-off between exploration and exploitation. So I'd like to maximize my cumulative reward. That means that I'd like to choose actions that I believe to be the best, that yield the highest rewards. But at the same time, I would like to learn those actions, so I need to try different alternatives, different actions. So how am I going to balance these two? That's a critical question. And actually this problem is called multi-armed bandit problem, and it has a certain reason. If you can see from this picture, this problem is inspired by slot machines in casino. So these machines have an arm. So when someone pulls the arm, it's going to yield a random reward. And they are called bandits because they are as good as stealing the money of the player as a bandit. So when you have multiple of them, it's called multi-arm bandits. And now the problem is when you should pull the machines. Okay, which machine you should pull. Okay, so the problem is this: in each round, so there's a gambler which must play one of the K machines. And at the beginning of each round, it receives a signal about the state of the environment that when it selects machine 80, it receives a random reward that comes from an unknown distribution. And the goal is to maximize the cumulative reward. Okay, so how can we measure the performance? What does maximizing the cumulative reward mean? So it's equivalent to actually minimizing what is called the regret. The regret means the loss due to not knowing. So it's the loss due to basically learning. So it's defined as follows. It is basically the difference between the expected reward of an oracle that knows perfectly everything. It knows the reward distributions, it can calculate the expected rewards, and picks for every context the action with the highest reward. It's the difference between this and what the learner acquires. So you expect the regret to grow over time. It cannot decrease, but you would like to minimize the growth rate of the regret. So here is a very simple example. Now consider the setting when I have only two actions. They generate this random reward sequence over time. And I know that the state of the environment, the context is A in the first 3 time slots and B in the last 2 time slots. So there's an oracle basically. Oracle knows the expected return of each arm, each action, given the context. So basically it looks at the context, it says that, okay, action 2 is better, so I'm going to pick that. When context is B, it looks at the expected rewards, it says that when context is B, action 1 is better, so I'm going to pick that. It does not care the randomness of the rewards. And the learner, of course, does not have this information here. And the only information it has is the rewards of the actions that it had selected. So it only observes these rewards in these red squares. And needs to compete with this oracle by just observing the random rewards in these red squares. Now what we would like from learning algorithm? We would like it to have a low regret. Basically, what does having a low regret mean? So, for instance, if you think of a Markov decision process kind of thing, what we have there is that we would like our policy to be optimal in terms of, say, average reward. So it corresponds basically to sublinear regret. If the regret grows sublinearly over time, its growth rate is bounded by t to the gamma less than 1. Then in terms of the average regret, we are going to achieve 0 average regret in the limit as the number of rounds go to infinity. Okay? But based on the application, we can achieve different types of regret. For instance, we can achieve bounded regret, which means that we converge to the average reward, optimal average reward, extremely fast. In some cases, we can only achieve logarithmic in time regret, which means very fast convergence. So we are only logarithmically worse than the optimal. Under some cases, we can achieve sublinear regret. Okay, this is also okay, it converges. But there might also be problems in which it's not possible to achieve sublinear regret, which means that we cannot learn efficiently. So ideally, we would like to achieve this. If not possible, this. If not possible, this. And there is a very important remark. So if, for instance, you consider a policy that basically looks at the empirical distribution of the rewards and chooses the action with the highest empirical reward, it's going to incur linear regret. So this means that if I always exploit based on what I believe to be best, I'm gonna have a very bad performance. Okay, so why need regret bounds? Because if we can have an online learning algorithm, we can bound its regret. That means that prior to deploying that algorithm in a real application, we know basically an upper bound on its loss. So we learn how well it works under given assumptions about the system without even deploying that. Of course, it's good in some applications because in some applications we would like to achieve guaranteed performance, so it's not a heuristic method. We'd like to basically exactly say that we are this far away from the optimum. And let me talk about, okay, you might ask the question, are these systems, okay, we talked about online learning, but where these systems are used in reality? Actually, there are current deployments of these systems. For instance, Google content experiments in which you optimize the contents of websites, or in Yahoo, personalized news article recommendation systems, or Microsoft's multi-word testing, which is an alternative to EE hypothesis testing. They use this bandit algorithms, and of course, personalized news on websites. So basically, its main use these days is personalized recommender systems. Okay. So I'm going to briefly mention some recent contributions, give some details of the algorithms and how they achieve the performance objectives. And I'm going to start with the most famous case, which is called the K-armed bandit. And actually, this problem has been studied since 1933, so it's a very old problem, basically. And I'd like to basically simplify the model I introduced earlier. So remember, I have this context vector. I just get rid of this, so there is no context vector. There are k actions, and whenever the learner chooses an action, it's going to observe a random reward that is drawn from some unknown distribution that only depends on the action. So this problem has attracted the attention of many researchers for many decades, and many different variants are solved. And perhaps the most simple algorithm that achieves good performance in this problem is what is called the upper confidence bound, UCB algorithm. So this algorithm is actually very simple to optimize, to maximize your cumulative reward. You only need to store the empirical mean reward, the sample mean reward of the actions, and the number of times you select each action. And the optimal policy is actually very simple. It's an index policy, which means that I'm going to compute an index for each action separately. And I'm going to choose the action that maximizes the index.
I'm sorry, I'm still following, because what did we assume about the statistics of METU?
Okay, so here, actually, that's a very good point. It's assumed that the reward of each arm is generated according to an independent and identically distributed process.
Okay, so it's not a restless.
Not the restless band, yeah.
Yeah.
In the IID. This is IID. Okay. So basically, the algorithm does the following. Now, I'm gonna choose at each time the action with the maximum index, where the index is sample mean plus an inflation term, and this term depends on logarithmically on the number of rounds, so it increases as the rounds increase, and it's inversely proportional to the number of times action A is selected. So basically, this term represents the uncertainty in my estimate, and I'm inflating the reward according to this uncertainty. So I'm basically optimistically saying that uncertain arms should have high rewards. And of course, if you select an action a lot of times, this is going to be big. So this is going to go to 0, so your index will be basically your sample mean. But if you don't select an action for a long time, this is going to be big. So you are going to explore that action. Okay, so this basically achieves the trade-off between exploration and exploitation. And there's a very nice theory behind the performance analysis. Basically, we can bound the performance regret of this UCB algorithm. And basically, its regret grows logarithmically in the number of rounds and is inversely proportional to the suboptimality gap, which is the difference between the expected rewards of the best and second best action. So this defines how hard your problem is. So if you have two actions that are very close to each other, it will take a long time to identify the best action. Okay, so, this is the case, but is it optimal? That's the question. And the answer is yes. Actually, it is proved earlier that this type of logarithmic growth cannot be avoided. So there is a gap between the learner and the oracle due to not knowing the expected rewards of each action. So although I use asymptotic notation here, actually there's a finite time equivalent of this bound, and as I said, this is optimal. This is the best one can achieve. Okay. So, what if we have more structure on the problem? Then can we achieve bounded regret? So this is what I considered in one of my works, and basically what I assumed is the following. Now, the expected return of an action depends on a global unknown parameter. So if I know the parameter, I can pick the best action at each time. So basically, I reduce the problem of learning to the problem of learning the global parameter. And basically, this type of learning under global parameter problems were studied before. For instance, one famous work is by Marcel and Sitsiklis. Basically, they assume that the reward is reward of an action is a linear function, unknown linear function of this global parameter, and they showed that bounded regret is possible. So, in one of my works, with my collaborators, basically we generalize this to nonlinear functions, basically to Hölder continuous functions in the parameter, and showed that we can achieve still bounded regret. And of course, what is the difference between log and bound? You might ask that question. And if you consider, for instance, a simple example of this, which is a dynamic pricing example, if I use an upper confidence bound policy, which is designed for independent actions, it's going to try to independently learn all of the actions, so it's going to incur a high regret. But if I use my policy that is learning the global parameter, it's going to incur a very small regret. So this is the difference between the bounded regret and the log regret if you draw it on a figure. Okay, so now I'm going to return back to the general case, which is the contextual bandit problem, which I described at the beginning. So this is my model. The learner observes a context, and the random reward of the action chosen by the learner depends on the context. And basically, this is the main thing I'm interested in. All the applications that I listed basically can be modeled as a contextual bandit. So, to solve this problem, people made different assumptions. So, one very common assumption is again to consider the IID case, independent identity distributed. So, what people assumed is this: I'm going to have the context and the rewards of each action come from a fixed distribution. So this vector comes from an IID process. Then they designed the algorithm and showed that actually you can achieve regret that increases square root in time, that increases logarithmically in the number of policies. So a policy is basically a mapping from a set of context to a set of actions. And then they show that under their assumption this is also optimal. But now consider the big data domain, and actually this method has several shortcomings, although it is very nice theoretically. One basically disadvantage is now if my context space, basically the number of different contexts is infinite, the number of policies that I have can also be infinite, right? So this bound will essentially not hold in that case. And this can happen if I have, say, continuous context. And what big data is, it's something that is dynamic, so the distribution of the data can change over time. The arrival rate of the context can change over time. So assuming that it comes from an independent and identically distributed process is basically not a very good assumption. Okay, so then people have proposed alternative ways to model this problem. And one other famous model is contextual bandits with similarity information. Here what happens is now the reward given the context. So if I fix the context, if I sample the reward, it's going to be IID. But the expected reward now will be a function of the context. So my reward distribution depends on the context. It's parameterized by the context, and I don't know that. And I don't need to assume any stochastic process that generates the context. They are arbitrary, non-stochastic. But I need to assume something, so I made this many relaxations. I need to put some restrictions. And there is a natural restriction which is called the similarity information, which says the following. The expected rewards of an action under similar contexts are similar to each other. So I can bound the difference between the expected rewards of an action as a function of the distance between the contexts. And this naturally happens in many problems in classification. If you have similar features, that means that your classifier is going to work in a similar way, do a classification in a similar way, and so on. Okay, so what is the best we can achieve under this setting? Actually, it is proven that in this setting, the regret can still be sublinear, but now the regret depends on the dimension of the context vector. So this is where curse of dimensionality happens. So when D is small, I can learn fast, but when D is large, this is almost linear, so I'm learning very bad. That's a trouble. So in one of my works, what I considered was, okay, I take the contextual bandit problem with similarity information, but let's consider the following setting. What if now my reward depends only on a subset of the context, which I call relevant contexts, instead of depending on the entire context vector. But I don't know what the relevant contexts are. So under this, I modeled a relevance relation, which is basically a mapping from the set of actions to the subset of the types of contexts. And this is what I need to learn, in addition to the expected rewards. And I also this as I described it previously. So here's a motivation. For instance, you would consider an application of medical treatment where there are different drugs or different dosage of drugs. There are different patient characteristics, and the effect of each drug maybe is only related to some of these characteristics. So it can be a 0-1, like effect, no effect type of thing, or it can be we can also add some noise to that. So it can be like this has less effect, this has strong effect. So for the case of zero-man effect, we can develop a learning algorithm with a regret bound that depends, whose time order only depends on the relevant context dimensions. So if D is large but the relevant is small, I'm going to learn much faster. I'm going to avoid the curse of dimensionality. And again, of course, you should do this when the relevant contexts are less than half of the total number of contexts that you have. And still you don't require this IID assumption. Okay. So now I have described the contributions and different types of bounds. I'm going to describe how the algorithms work for the context-dependent space. First of all, how we can use the similarity information. This is given to us, how we can use this information to learn in a fast way. Now, first of all, if you try to learn the rewards of action for each context separately, it's going to take a very long time, right? Because you might never observe a context that you have observed before in the future, because there are too many contexts. And the most important thing in using the similarity information is to basically discretize in some way or partition the space of contexts. Okay, so the idea is I basically partition the context space, and what I'm going to do is that I'm going to learn the rewards of the actions in each set in the partition by only looking at the past observations within that set. So it means the following: the instances that falls into P are going to be similar in some way to each other. So if I just average over these instances, I'm going to get a good estimate of what's happening for individual contexts that fall into this region. Of course, this can be done in a way to balance the trade-off between how many samples you can use to estimate the rewards and how dissimilar are those samples. For instance, if I use a larger set, and if I average over a larger set, I'm guaranteed to get more past observations in that set. So basically, my accuracy will improve because of that. But the instances here will be more dissimilar. So I'm going to have an approximation error due to that, using a larger set in the partition. Okay? So, of course, an algorithm that learns must need to balance the granularity of this partition very well. And of course, the algorithm must also adaptively basically partition the context space. So as more data arrives in an online manner, the algorithm should zoom into the regions where there is larger number of data arrivals to make more accurate estimations of these regions. Okay? So basically this is what happens as time passes. So I can also show it like this. So you can use balls, and as time passes, based on where the contexts arrive, you generate balls. But as more arrivals happen, the balls you generate basically get smaller in radius so that you get more accurate estimations in those regions of the space. Okay, this is how to use similarity information. Now I'm going to explain how we can balance the trade-off between exploration and exploitation. Basically, I already told one method, which was the UCD method, but I'm going to tell other methods as well. Now, the main problem is most of the time we would like to take the action that maximizes our empirical reward. But occasionally we would like to explore other actions to learn more about what other actions are. And there's a very justified reason for this. For instance, consider this example. Assume that I estimated rewards of two actions, action 1 and action 2, and the estimated rewards are these black squares. Now these are estimates, so I have uncertainty about them, right? So I can then find a confidence interval over the estimated reward of each action based on the number of times I selected that action. For instance, this is my confidence interval for action 1. That means that the true reward of action 1 lies in this interval with high probability. And this is my confidence interval for action 2, which means that the true reward of action 2 lies within this interval with high probability. So now consider this. I have the estimated reward of action 2 much smaller than estimated reward of action 1. But this does not imply that the true reward of action 2 is less than the true reward of action 1. If you look at here, the upper confidence bound, for instance, action 2 might actually have a true reward that is higher than action 1's true reward. So that means that I should explore action 2. Okay? The optimistic estimate of action 1 is here, action 2 is here. Although the sample mean rewards are different, in different order. Okay? So, of course you can do this exploration in many different ways. So one way I'm also going to mention is that you just keep a control function, you say the following: if I play action A less than some monotonic increasing function of time, if I do not select the action A lot, I'm just going to play it. If all the actions are selected enough, I'm going to just play the empirical best action. Or you can use the UCB, which I described in the earlier slides. Or there is a recent method which has become very popular recently due to the fact that its theoretical analysis is performed. Actually, this is proposed many decades ago, but the theoretical analysis is very new. The idea is basically take a Bayesian approach. What I can do is I can compute a posterior distribution over the rewards of actions based on my history, and I'm going to select an action based on its probability of being optimal given the history. So all three methods, so this is more like you select actions deterministically given the history. Here you select actions deterministically given history. Here you select actions in a random fashion given history. All these methods can achieve sublinear regret, but they have different trade-offs. Okay, so if I combine all these methods that I talk about, I can come up with a contextual online learning algorithm, COLA. Basically, the idea is very simple. I just, when a new user comes at time t, I'm just going to find out which past information to use by identifying the set in the partition of the context space that this new context belongs to. So I'm going to use the rewards estimates that I have here, and can also, based on how many times I select each action, form a confidence estimate for each action. Then based on this, I choose to exploit or explore, and then after that, given the random reward feedback, I basically update my estimates. So I do not need to store all past observations here, just the estimates. Okay?
We have about 2 minutes.
Okay, this is very good. So I was also going to basically talk about how we can learn the relevant context, but let me just go over it in 1 minute. So the idea was to, if you want to reduce the curse of dimensionality, we basically can form a relevance test which says the following. So if my reward only depends on if my reward only depends on the context which has a type of age, then if I average over all age and say weight contexts, what I should obtain should be similar to what I will obtain if I average over all age and say blood sugar level contexts. So using this fact, I can design a relevance test that learns which contexts are relevant to my actions, and I can use it together with my online learning algorithm to basically reduce the curse of dimensionality problems. So in a high dimensional space, if instead of forming this partition over this entire high dimensional space, I can just form partitions of lower dimensional subspaces and use the estimations obtained in the lower dimensional high spaces basically to choose the actions. Okay? So basically I can obtain bounds on the performance for this case that only depends on the number of relevant context dimensions. And of course, when you learn the relevance, your performance will significantly improve, and you can test this also numerically. So let me basically conclude. I just gave an introduction on this online learning problems, the challenges in big data, and how these contextual bandit problems can address those challenges, how we can have performance bounds, and how we can develop those type of algorithms. And I'd like to conclude with several important research directions. So some of these I'm currently working on, and some of these are also research directions in which researchers are currently working. So one problem is, for instance, observing the data can also be costly, right? So I said that the context is available, but what if it is not available? So can you also choose what to observe and define a performance metric according to that to optimize? The other challenge is learning the similarity information. So I said that in contextual balance, the similarity information is given, it is known. But how can we learn it?